I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines and the relentless rush of now, and step quietly into the vast, starlit corridors of cosmic possibility, where questions stretch back not thousands of years but billions, where the story isn't written in history books or carved in monuments, but traced in the light of distant suns still travelling toward us across the void. Here, in this space between present and infinite, we wander together through one of humanity's oldest dreams. We stand at the edge of our solar system, that familiar neighbourhood of planets and moons and asteroid belts, and we ask a question that feels both simple and impossible. Can we ever leave? Can we slip beyond the sun's embrace, beyond the invisible boundaries that have held us since our species first looked up, and venture into the darkness between stars? Each episode here isn't just about rockets and trajectories. It's not about memorising distances or cataloguing spacecraft. It's about the human desire to explore beyond every horizon, the scientists dedicating lifetimes to questions that may not have answers, the engineers building machines that will outlive us all. It's about one of the most profound challenges humanity has ever contemplated, where the distances are so vast that even light itself takes years to cross them, and where everything we thought possible about travel is quietly, beautifully challenged. If you enjoy these quiet journeys beyond our world, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. When we speak about leaving the solar system, it helps to first understand what we would be leaving behind. Our solar system is not just a collection of planets arranged neatly around a star. It is a vast and intricate structure, a cosmic neighbourhood that has been humanity's only home since the first human opened their eyes to the sky. Every memory we carry, every story ever told, every civilization that has risen and fallen, all of it has taken place within this narrow band of warmth, circling a single ordinary star we call the Sun. The Sun itself dominates everything. It accounts for more than 99% of all the mass in the solar system. Its gravity holds every planet, every asteroid, every distant comet in orbit. Its radiation bathes every surface, shaping atmospheres and driving weather patterns. Its storms of charged particles wash over planetary magnetic fields, painting auroras across alien skies. Without the Sun, Earth would be a frozen rock drifting silently through the void. Without its steady fusion, pouring energy outward in all directions, life as we know it could never have emerged. Orbiting this star are the planets, each one a world with its own character. Closest to the Sun is Mercury, small and scorched, racing through its orbit in just 88 days. Venus follows, wrapped in a suffocating blanket of carbon dioxide, its surface hot enough to melt lead. Then comes Earth, a rare balance of warmth, liquid water and chemistry, the only place where we know for certain life has taken hold. Mars is smaller, colder, drier, but still intriguing enough that we send robots to comb its surface for clues about its past. Beyond the rocky inner planets lies the asteroid belt, a scattered ring of debris left over from the solar system's formation. Then come the giants. Jupiter is so large it could swallow all the other planets combined. Its storms have raged for centuries, and its many moons form a miniature solar system of their own. Saturn spins farther out, adorned with rings of ice and dust that stretch tens of thousands of kilometres, yet remain only meters thick. Uranus tilts on its side, rolling rather than spinning, while Neptune howls with winds faster than any found on Earth. But the solar system does not end with the planets. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies stretching outward for billions of kilometres. Pluto resides here, no longer called a planet, but still a fascinating world of frozen mountains and nitrogen ice. Farther still, perhaps 1,000 times more distant than Neptune, lies the Oort Cloud, a spherical shell of comets surrounding the entire solar system. This cloud marks the true outer boundary, where the Sun's gravity still holds sway but only barely. The objects here drift in darkness so complete that the Sun appears as little more than a bright star among many. To leave the solar system fully would mean passing even the Oort Cloud, crossing into interstellar space, where the influence of our sun fades into the background hum of the galaxy. The distances involved are staggering. Light from the sun takes just over 8 minutes to reach Earth, but more than 4 hours to reach Neptune. At the edge of the Oort Cloud, that light might take more than a year to arrive. If you could drive a car at highway speed straight outward, it would take you nearly 6,000 years just to reach Pluto, and hundreds of thousands more to clear the Oort Cloud entirely. Our solar system is not just a physical space, it is also the cradle that has shaped everything we are. The very elements in our bodies, carbon and oxygen and iron, were forged in earlier stars and gathered here in this specific system, condensed into Earth and eventually into us. Our calendars are based on Earth's orbit around the Sun. Our concept of time itself is measured by the turning of our planet. Our myths and histories are filled with stories about the Sun, the Moon and the visible planets. To speak of leaving the solar system is not just to speak of travel. It is to speak of leaving behind the context that has defined what it means to be human. And yet the boundaries are there, waiting. Beyond. The last faint tug of the Sun's gravity lies interstellar space, where stars are scattered like islands in a cosmic ocean. Each star has its own system of planets, asteroids and comets. To cross into that space would be to leave behind the only port we have ever known. Our solar system is both home and horizon, the familiar and the boundary all at once. It stretches from the fiery furnace of the Sun's core to the icy edges where comets slumber in darkness. It contains worlds both hostile and inviting, mysteries solved and mysteries waiting. It is at once vast enough to humble us and intimate enough to feel personal. As we think about the possibility of leaving, we should take time to reflect on what it means to remain. To travel outward is to measure ourselves against the scale of this place, to ask whether our engines and our patience can match the distances involved. Our solar system is the only home humanity has ever known, a bubble of warmth in the cold expanse of space. Understanding its true size and structure is the first step in comprehending the challenge that lies ahead. When people talk about leaving the solar system, the first question that often arises is deceptively simple. Where exactly does the solar system end? The answer depends on who you ask, because the boundaries of our home in space are not as sharply defined as the border of a country or the shoreline of an island. They are fuzzy, layered, and sometimes invisible to human senses. It is a bit like standing in a forest and asking where the forest ends. Is it the last tree, the edge of the undergrowth, or does it extend to where the soil stops being shaped by its roots? The solar system is much the same, full of thresholds that overlap and stretch outward, each one offering a different idea of what it means to say here is the edge. The most familiar boundary is perhaps the orbit of the outermost planet. For a long time, that was Pluto. When it was discovered in 1930, Pluto became the marker of the solar system's edge in the public imagination. Beyond it, the map seemed to fade into blankness. But as telescopes improved, astronomers discovered many more icy bodies in the same distant region, some nearly as large as Pluto itself. Together, they formed what is now known as the Kuiper Belt, a wide ring of frozen worlds and fragments extending far beyond Neptune. The Kuiper Belt itself stretches outward for perhaps 50 astronomical units, an astronomical unit being the distance from Earth to the Sun, about 150 million kilometres. That means the belt lies billions of kilometres away, a realm of frozen rock and ice that has remained relatively unchanged since the early days of the solar system. If you wanted to call that the edge, you could, but it would only be the first edge, not the last. Far beyond the Kuiper Belt lies another even more mysterious boundary, the Oort Cloud. Unlike the Kuiper Belt, which is shaped like a flattened disk, the Oort Cloud is thought to form a vast spherical shell of icy bodies surrounding the solar system in every direction. These objects are so far away that they may take hundreds of thousands of years to complete a single orbit around the Sun. Some estimates place the outer edge of the Oort Cloud nearly halfway to the next star. If the Kuiper Belt is a distant backyard, the Oort Cloud is a fence line so far away it is almost lost in the haze of the galaxy. The Oort Cloud has never been seen directly. Its existence is inferred from the behaviour of long-period comets, those icy travellers that swoop in from far beyond Neptune. sometimes taking tens of thousands of years to return. The orbits of these comets suggest they come from a vast, distant reservoir, a place where countless icy bodies drift quietly until some gravitational nudge sends them inward. In this sense, the Oort Cloud is an edge we cannot see, a boundary painted in mathematics and inference rather than direct observation. But there are other edges too, defined not by rocks and ice but by forces. One of the most important is the heliosphere, the bubble created by the solar wind. The sun constantly emits a stream of charged particles flowing outward in all directions at hundreds of kilometers per second. This wind shapes a bubble around the solar system, pushing against the thin gas of interstellar space. Inside this bubble, the solar wind dominates. Outside it, the gas and dust between stars take over. The boundary where these two pressures balance is called the Heliopause, and it represents another kind of edge. Unlike the Oort Cloud, the Heliopause is something we have actually touched, at least with instruments. In 2012, Voyager 1 crossed into interstellar space by passing through the Heliopause, becoming the first human-made object to leave the solar wind's domain. Its instruments detected a sudden increase in the density of charged particles along with a change in magnetic field direction. It was like stepping across an invisible line, one that had been theorized for decades, but never experienced directly. Voyager 2 followed in 2018. Together, these two spacecraft gave us our first measurements of a boundary that is both intangible and real, marking the edge of the sun's direct influence. Still, even the Heliopause is not necessarily the true end of the solar system. The sun's gravity extends far beyond it, holding the Oort Cloud in place. The sun's light reaches farther still, albeit faintly, before blending into the general glow of the galaxy. And even beyond all that, the influence of our star can be detected in more subtle ways, like its motion through the Milky Way, carrying the planets and clouds along with it. The edges are less like walls and more like gradients, each one fading into the next. This layered nature of boundaries means that the solar system does not have a single endpoint. Instead, it has many, each one depending on the context. For a planetary scientist, the edge might be Neptune or the Kuiper belt. For a heliophysicist, it might be the Heliopause. For a dynamicist studying comets, it might be the Oort Cloud. For a dreamer imagining journeys to the stars, it might be wherever the sun's pull finally gives way to another star's. None of these answers is wrong. They are simply different ways of looking at the same reality, each shaped by what we are trying to measure or understand. The difficulty of pinning down the boundaries also reflects the complexity of the solar system itself. For centuries, people thought of it as a neat arrangement of planets orbiting a central sun, like beads on a string. But the more we study, the more we find layers upon layers, structures within structures. The solar system is not static but dynamic, evolving with time, and the edges we define today may shift as our understanding deepens and our instruments reach farther into the darkness. Why did humans start dreaming of leaving Earth in the first place? What was it about the stars that stirred us to think beyond the safety of the ground? Long before rockets, before telescopes, even before written language, human beings looked at the night sky and wondered what it meant. The stars were constant companions, scattered across the darkness with a persistence that must have felt mysterious to early eyes. Fires could burn out, rivers could dry, mountains could crumble, but the stars remained. They moved in patterns, slowly and predictably, almost as though they were alive. To the earliest humans, those lights were both comfort and puzzle, far away yet always present. And so the dream of leaving Earth did not begin with science. It began with imagination. Evidence of that imagination appears in the oldest myths. Many cultures pictured the sky as a dome or a canopy, something resting above the world like a ceiling. The stars were thought to be holes or lamps placed there by gods or ancestors. Some traditions spoke of stairways or ladders that could reach the heavens. Others imagined great birds carrying souls skyward, or trees so tall their branches touched the stars. These were not literal blueprints for spaceflight, but they reveal something essential. Humans have always wondered whether the sky was simply a view or whether it was a place one might go. Over time, stories grew more elaborate. In Mesopotamia, the Epic of Gilgamesh described journeys to distant realms, including the skies. Ancient Egyptians envisioned the soul sailing with the sun god Ra in his boat across the heavens. In Greece, myths told of heroes and mortals lifted to the stars, transformed into constellations as a kind of immortality. The Polynesians, masters of navigation, treated the stars as guides across the ocean, showing that even without technology, humans already used the heavens as a map. These cultural memories, though different in detail, shared a common theme. The sky was not only above but beyond, a place where stories could travel, and maybe someday people too. Philosophers also wrestled with the idea. In the 4th century before the Common Era, Aristotle argued that the heavens were perfect and unchanging, made of a special substance different from the earth. To him, the stars were eternal and unreachable, but not everyone agreed. A few thinkers speculated that Earth might not be the centre of everything, that the stars could be other suns, perhaps with their own worlds. Such ideas were radical, often dismissed or forgotten, yet they planted seeds. To imagine the stars as places rather than lights was the first step toward dreaming of journeys to them. As centuries passed, tools changed the way people looked at the night. With the invention of telescopes in the early 1600s, the sky transformed from a distant mystery into a closer, more detailed landscape. Galileo's observations showed that the moon was not a perfect glowing disk, but a world with mountains and craters. Jupiter had moons of its own, orbiting like miniature planets. Saturn had strange appendages, later understood as rings. These discoveries shattered the idea of perfect, unreachable heavens. They revealed that the sky was full of worlds, perhaps not so different from Earth. For the first time, leaving Earth did not seem entirely impossible. It seemed like an extension of exploration. During the Renaissance and Enlightenment, thinkers began to imagine mechanisms that could take humans upward. Some envisioned vast towers or mechanical birds. Others thought of balloons filled with special gases, centuries before hot air balloons were invented. In literature, writers started crafting tales of voyages to the moon. One early example is The Man in the Moon, published in 1638, which described a character carried upward by a flock of geese. A little whimsical perhaps, but it showed how seriously people were beginning to consider the possibility of travel beyond Earth. Science and storytelling were becoming partners in the dream. By the 19th century, with the rise of industrial technology, the dream took on more mechanical forms. Writers like Jules Verne described giant cannons that could shoot capsules to the moon, complete with windows for travellers to peer out into space. Though unrealistic, these stories fired the imagination of generations. Meanwhile, science itself was advancing. Isaac Newton's laws of motion and universal gravitation, published in the 17th century, had already provided the mathematics to describe orbits and trajectories. For the first time, humans could calculate not just that the moon circled Earth, but why it did so, and how one might in theory escape gravity. The math was clear. To leave Earth, an object would need enormous speed, what we now call escape velocity. The challenge was energy. How could anyone build a device powerful enough to provide that speed? For centuries, this remained unsolved. The dream was alive, but it stayed in the realm of imagination. In the early 20th century, a few visionaries began to bridge the gap. One of the most important was Konstantin Tsiolkovsky, a Russian schoolteacher who became the father of astronautics. He was the first to write in detail about rockets as a means of space travel. Using Newton's laws, he derived the rocket equation, showing how speed could be achieved by ejecting mass at high velocity. He imagined multi-stage rockets, space stations, and even human colonies beyond Earth. At a time when powered flight was still new, Tsiolkovsky's ideas seemed fantastical, but they were grounded in real physics, and they shifted the dream from myth to engineering. Others followed. In Germany, Hermann Oberth and later Werner von Braun developed practical designs for rockets. In the United States, Robert Goddard launched some of the first liquid-fueled rockets, small and modest, but proof that theory could become hardware. These pioneers often faced ridicule. Newspapers mocked Goddard's ideas of rockets reaching the moon, calling them science fiction. Yet within decades, his vision would become reality. The dream was growing teeth. By the mid-20th century, global events accelerated the dream. The Cold War rivalry between the United States and the Soviet Union poured resources into space exploration. In 1957, the Soviet Union launched Sputnik, the first artificial satellite. Just 4 years later, Yuri Gagarin became the first human to orbit Earth. Suddenly, leaving Earth was no longer a matter of stories or mathematics. It was happening. When we think about journeys across Earth, distance is something we measure in hours or days. A walk across a town might take minutes, a drive across a country might take a few days, and a flight around the globe might take less than a day. Even the largest distances on our planet feel manageable within the rhythm of a single life. But when we lift our eyes to the stars, distance becomes something else entirely. It becomes a scale so vast that our normal ways of measuring time and travel begin to fall apart. This is where the universe humbles us most clearly. Consider again the nearest star system, Alpha Centauri, just over 4 light-years away. It is our closest neighbour, the stone's throw of the galaxy. If you were to drive there in a car moving at highway speeds, never stopping, it would take more than 50 million years. Even at the speed of the fastest spacecraft humanity has ever launched, the journey would take over 70,000 years. To us, those are not practical numbers. They are geological timescales, spans of time more suited to the rise and fall of mountains than to the planning of missions. And that is only the nearest star. Beyond Alpha Centauri lie thousands of others, each one farther than the last, each one demanding patience greater than anything humans have ever attempted. When astronomers talk about distance in the universe, they use units like the light year or the parsec. A light year is nearly 10 trillion kilometers. A parsec is a little over 3 light years. These units were invented because kilometers and miles quickly become too small to be useful. If we were to measure the distance across the Milky Way in kilometers, the number would have 20 digits. Even saying it out loud would feel absurd. So we scale upward, inventing larger units, but the immensity remains. The Milky Way is about 100,000 light-years across. Light, moving at nearly 300,000 kilometers per second, takes 100,000 years to cross it. Imagine a beam of light, leaving one edge when humans were still painting caves in Europe, and only now reaching the middle. The scale bends our minds not only because the numbers are large, but because they defy our intuition about travel. We are used to thinking of journeys as things we can complete, things that fit within a life. But interstellar distances often cannot be completed in that way, at least not with current technology. They require us to imagine journeys where the departure and arrival are separated, not by years but by generations, or even by epochs. This shift in perspective is difficult, but it is also part of the wonder. It forces us to see ourselves as small and temporary against the backdrop of a universe that is vast and enduring. The distances also affect how we think about communication. On Earth, messages can circle the globe in less than a second. In space, even signals moving at light speed face delays. A message to Mars may take minutes to arrive. A message to Alpha Centauri would take over 4 years. A conversation across such a gap would be impossible in the way we understand conversations. By the time a question was asked, the person who asked it might no longer even be alive when the answer returned. In this way, distance reshapes not only travel but also connection, changing the very meaning of dialogue and exchange. And then there are the galaxies. Beyond the Milky Way lies Andromeda, the nearest large galaxy, about 2 million light-years away. The light we see from it tonight left when early humans were first beginning to use stone tools. To travel there at the speed of Voyager would take longer than life has existed on Earth. And Andromeda is close compared to most galaxies. The observable universe stretches nearly 90 billion light-years across, filled with hundreds of billions of galaxies. The scale is so enormous that our minds can barely hold it, a panorama of distance that stretches beyond imagination. This immensity raises questions that are as emotional as they are scientific. If the distances are so great, can we ever hope to cross them? Will humans, or anything descended from us, ever walk under the light of another star? Or are we bound to remain within our solar system, explorers of only our local neighbourhood, forever gazing across an ocean too vast to sail? Some see these distances as barriers, insurmountable walls. Others see them as challenges, invitations to dream larger and to think beyond the limits of current technology. What is certain is that distance defines our place in the cosmos. The sun may feel central to us, but it is only one star among hundreds of billions, scattered across a disk so wide that even light takes millennia to cross it. Our nearest neighbours are close in cosmic terms, but distant enough to humble our ambitions. To leave the solar system is already a staggering goal. To cross to another star is greater still. To dream of other galaxies is to step into the realm of imagination itself. And yet, even as these distances bend the mind, they also expand it. To grasp the scale of the universe is to see ourselves in a new light. We become small, yes, but also part of something immense. The fact that we can even measure these distances, even think about them, is itself remarkable. Our minds may bend, but they do not break. We learn to hold these vast numbers, to carry them in thought, to let them guide our sense of what is possible. When we confront the distances between stars and galaxies, the challenge seems almost absolute. Tens of thousands of years to reach even the closest systems with today's technology. Millions to cross between galaxies. It is natural then to ask whether there might be another way, not moving faster through space, but reshaping space itself. Yet for now, the distances remain, patient and unchanging, a reminder that the universe is not built for human convenience. Stars are far apart whether we like it or not. If we wish to travel among them, we must adapt our expectations to their scale, not demand that they shrink to ours. The contradiction is this: we dream of leaving, but the distances mock those dreams. We imagine journeys, but the timescales dwarf our lifespans. We reach outward, but the void stretches farther still. And yet the dream persists, stubborn and enduring, because curiosity does not quiet itself easily. When people imagine leaving the solar system, the first image that usually comes to mind is a rocket, a tall cylinder rising slowly from the launch pad, engines igniting with thunder, fire pouring downward as the vehicle climbs toward the sky. It is a familiar picture, one that has defined space exploration since its earliest days. But rockets are more than dramatic symbols. They are the only machines we currently have that can push matter out of Earth's atmosphere and onward into the deep. And to understand whether we might someday leave the solar system, we have to understand what rockets can and cannot do. At the heart of any rocket lies a simple principle: action and reaction. A rocket moves forward by throwing something backward. It expels mass at high speed, and the equal and opposite reaction pushes the rocket in the other direction. This idea is not new. It traces back to Newton's third law of motion, formulated in the 17th century. But while the law itself is simple, making it practical for space travel has been anything but easy. To escape Earth, a rocket must carry not only its payload, but also the fuel it will burn, and often the fuel required to lift that fuel, in an endless cycle of weight and energy. This is the challenge that every space mission must solve. The speed required to leave Earth is immense. From the surface, a spacecraft must reach about 11 kilometers per second to escape Earth's gravity completely. That is more than 40,000 kilometers per hour, far beyond anything a car or plane could ever achieve. And that is only the first hurdle. To escape not just Earth but the Sun, an object must reach about 42 kilometers per second relative to the Sun's pull. That is nearly 4 times faster. It means that leaving the solar system requires a velocity so great that no human spacecraft has yet been able to achieve it directly. Instead, we use clever techniques like gravity assists, borrowing momentum from planets to fling probes outward at higher speeds. Still, rockets remain the only launch system we have. The history of space exploration is filled with names of rockets that became milestones. The Saturn V, which carried astronauts to the moon, was one of the most powerful machines ever built. It stood taller than a 30-story building, burned fuel at an astonishing rate, and produced enough thrust to lift 3 men and their equipment all the way to lunar orbit. Later rockets like the Space Shuttle, Ariane, Proton and Falcon 9 carried satellites, telescopes and supplies. But the principle remained the same. Enormous energy expended in a few minutes, just enough to push fragile cargo into orbit. When we think about leaving the solar system, though, even these mighty machines look small. The Saturn V could send a few tons of equipment to the moon, but interstellar distances require far more endurance. Chemical rockets, which burn liquid hydrogen, oxygen, kerosene or similar fuels, can produce powerful thrust, but they are inefficient for long journeys. Once their tanks are empty, the spacecraft must coast, carrying no further means of acceleration. For short missions within the solar system, this is acceptable. For journeys that might take centuries, it is not. This is why engineers and scientists have looked at alternative engines. One option is nuclear propulsion. Instead of burning chemical fuels, a nuclear thermal rocket would use a reactor to heat hydrogen, expelling it at high speed. Such designs could in theory achieve higher efficiency than chemical rockets, reducing the amount of fuel required. Experiments were even conducted in the mid-20th century, under programs like NERVA, which built and tested prototype reactors. They worked, but political and safety concerns prevented them from flying. Still, nuclear propulsion remains one of the most realistic ways to shorten travel times in space. Beyond thermal systems, there are nuclear electric, say, designs where a reactor generates electricity to power ion thrusters. Ion engines work by accelerating charged particles, usually xenon ions using electric fields. They produce very little thrust, sometimes no more than the weight of a sheet of paper resting on your hand. But they can run continuously for months or years, gradually building up high speeds. NASA's Dawn spacecraft, which explored the asteroid belt, used such engines to great success. While too weak for launch from Earth, ion drives are excellent for long steady pushes once a spacecraft is already in space. For journeys to the edge of the solar system, they may be among our best tools. Another possibility is solar sails. These are large, thin sheets of reflective material that use the pressure of sunlight itself to provide thrust. Photons carry momentum, and when they bounce off a reflective surface, they transfer that momentum to the sail. The push is tiny but constant, and unlike a rocket, it requires no fuel. Once deployed, a solar sail can keep accelerating as long as light shines upon it. Missions like Icaros from Japan and the Light Sail projects funded by private foundations have already demonstrated that this principle works. In theory, a sail large enough and light enough could eventually reach interstellar speeds, though the engineering challenges are enormous. Looking even further, there are concepts that sound almost like science fiction but are grounded in real physics. One is the idea of laser-pushed sails, where powerful lasers on Earth or in orbit shine on a spacecraft's sail, driving it forward much faster than sunlight alone. This idea has attracted serious attention from projects like Breakthrough Starshot, which imagine sending tiny probes to the nearest star system within a human lifetime. If built, such a system could accelerate small craft to a fraction of the speed of light. But again, the challenges are immense, involving massive energy requirements, precision targeting, and materials that can withstand intense acceleration. Then there are fusion engines which would harness the same process that powers the sun. Fusion reactions release enormous amounts of energy by combining atomic nuclei, and if controlled, they could provide sustained thrust for long voyages. Many designs have been proposed, including magnetic confinement and inertial confinement approaches. One famous concept, Project Daedalus in the 1970s, envisioned a fusion-powered starship that could reach nearby stars within a few decades. While no working fusion rocket exists yet, research into fusion for power generation continues, and any breakthroughs could someday spill over into propulsion. When people talk about humanity's first steps into interstellar space, the story usually turns to two small spacecraft launched in the late 1970s. They were not the largest or the most advanced machines we have ever built. In fact, by today's standards, they seem almost fragile. Their computers are weaker than the phone you may carry in your pocket. Their cameras and instruments, though groundbreaking at the time, are simple compared to what modern probes can carry. And yet, these two spacecraft, Voyager 1 and Voyager 2, have become symbols of something far greater than their hardware. They are the first messengers to leave the solar system, carrying with them not only scientific instruments, but also fragments of human culture, like messages in bottles cast into a cosmic sea. The Voyagers were launched just weeks apart in 1977, timed to take advantage of a rare planetary alignment that occurs only once every 176 years. Jupiter, Saturn, Uranus and Neptune were positioned in such a way that a single spacecraft could visit them in sequence, using each planet's gravity to sling itself toward the next. This technique, called a gravity assist, allowed the probes to achieve far greater speeds than rockets alone could provide. It was as if the planets themselves were lending a hand, giving the Voyagers the momentum they would need to escape the Sun's grasp. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th. Their trajectories were carefully planned. Voyager 2 would take the Grand Tour, visiting all 4 outer planets. Voyager 1 would move more directly outward, passing by Jupiter and Saturn before curving above the plane of the solar system. Together, they would provide humanity with its first close-up views of worlds that had previously been no more than distant points of light. And what views they were! Voyager 1 revealed the intricate structure of Jupiter's clouds, the swirling patterns of its storms, and the volcanic activity of its moon Io, the first time active volcanoes had been observed beyond Earth. Voyager 2 continued the journey, sending back images of Saturn's rings in detail never seen before, then pressing on to Uranus and Neptune. These encounters transformed our understanding of the outer planets. We learned of new moons, complex ring systems, unexpected magnetic fields, and dynamic atmospheres. For the first time, these distant giants became places, not just points in the sky. Yet even as the Voyagers sent back data that reshaped planetary science, they were also carrying something less tangible. On each spacecraft, bolted to the side, is a golden record, a phonograph record made of copper, coated with gold, designed to last for 1 billion years or more in the cold of space. The record contains sounds and images chosen to represent Earth and humanity, greetings in 55 languages, music from different cultures from Bach to Chuck Berry, the sounds of rain, thunder and birdsong, photographs of landscapes, animals, people and mathematical diagrams. Instructions are etched into the record itself, explaining how to play it, how to interpret the data, and how to locate Earth in the galaxy using pulsar maps. The golden record was the brainchild of a team led by Carl Sagan. The idea was simple but profound. If the Voyagers were destined to drift forever in interstellar space, why not send them as ambassadors as well as probes? Why not attach a message that could, however unlikely, someday be discovered by another intelligence? It was an act of both science and imagination, of humility and hope. No one expected aliens to stumble across the record anytime soon. The galaxy is vast, and the chance of an encounter is slim. But the gesture itself was meaningful. It was humanity declaring we were here. This is what we sounded like. This is what we looked like. This is what we valued. In many ways, the golden records are the most poetic part of the Voyagers. The spacecraft themselves will someday fall silent, their power sources too weak to keep instruments running. Already, NASA has been shutting down non-essential systems to preserve energy. By the 2030s, both Voyagers may be entirely quiet, but the records will remain, attached to their silent hulks, drifting through interstellar space long after Earth has changed, long after the civilizations that built them have faded. In that sense, they are time capsules, not just of technology, but of humanity itself, frozen moments of who we were at the close of the 20th century. Voyager 1 is currently the farthest human-made object from Earth. It crossed the Heliopause in 2012, entering interstellar space, and continues to move outward at more than 17 kilometers per second. Voyager 2 followed in 2018, taking a slightly different path, but now also outside the heliosphere. The distances are staggering. Voyager 1 is more than 150 astronomical units from Earth, over 20 billion kilometers away. Its radio signals, travelling at the speed of light, take more than 22 hours to reach us. When controllers send a command, nearly 2 days pass before they see the result. And yet, against all odds, the spacecraft still respond, their faint whispers detected by giant antennas of the deep space network. The persistence of the Voyagers has surprised many. Designed for a 5-year mission, they have lasted nearly half a century. They have endured the cold, the radiation, and the emptiness, continuing to function far beyond their expected lifetimes. Each time they send back data, It is a reminder of how far a small piece of human engineering can go. They are proof that our reach already extends beyond the solar wind, into the thin plasma between the stars. But perhaps their most enduring legacy is not scientific, but symbolic. The Voyagers are not fast enough to reach another star in any reasonable timescale. At their current speed, it would take tens of thousands of years to approach even the nearest systems. They will never arrive at a destination, never land, never send back images of alien worlds. They will drift, silent and unseen. And yet, because of the golden records, because of the stories we attach to them, they feel alive in a way that other spacecraft do not. They are more than machines. They are emissaries, carrying human voices into the dark. When we imagine the edge of the solar system, it is natural to think of something visible, a line drawn across space where the sun's domain simply ends. But the reality is more gradual, more diffuse, and perhaps more mysterious than any simple border could suggest. One of the most important boundaries is not made of rock or ice, but of wind and plasma. It is called the Heliopause, and it may be the truest marker of when a spacecraft has left the solar system. The story begins with the solar wind. From its outer layers, the sun constantly emits streams of charged particles, mostly protons and electrons, racing outward at hundreds of kilometers per second. This flow of plasma creates the heliosphere, a vast bubble surrounding the sun and all its planets. Inside the heliosphere, the solar wind dominates, pushing against the thin gas and dust of the interstellar medium. Outside it, the influence of other stars and the galaxy itself begins. The boundary between these two regions is the heliopause, the point where the outward pressure of the solar wind balances with the inward pressure of interstellar plasma. Though invisible, the heliopause is enormous. Its distance from the sun is not fixed, because the strength of the solar wind changes with the sun's activity and with the conditions of the interstellar medium. On average, it lies somewhere around 120 astronomical units from the sun, or about 18 billion kilometers. To put that in perspective, Earth orbits at 1 astronomical unit. Neptune, the farthest planet, lies at about 30. The heliopause is 4 times farther than Neptune, an edge so distant it took the Voyager probes more than 3 decades to reach it. When Voyager 1 crossed the heliopause in 2012, it became the first human-made object to leave the protective bubble of the sun. The transition was not marked by any visible sign. There were no walls, no glowing barrier. Instead, the spacecraft's instruments detected changes in the environment. The density of charged particles increased, indicating it had entered the interstellar medium. The magnetic field shifted in direction. The stream of solar particles dropped sharply. Voyager 2, travelling on a different path, crossed the heliopause in 2018, confirming that the boundary was real and not just a theoretical construct. Together, they provided humanity with its first direct measurements of interstellar space. Crossing the heliopause is significant because it changes the kind of space a spacecraft inhabits. Inside the heliosphere, the solar wind shields us from much of the cosmic radiation that permeates the galaxy. Outside, that radiation is stronger. Inside, the sun's influence dominates. Outside, the environment is shaped by the larger structure of the Milky Way. In a sense, the heliopause is the skin of the solar system, the point where the inside ends and the outside begins. To leave it is to truly step into the galaxy. Yet the heliopause is not a sharp edge. It is more like a transition zone, a region where solar and interstellar influences mingle and compete. Scientists speak of the termination shock, the point where the solar wind slows down abruptly as it encounters resistance. Beyond that lies the Helios sheath, a turbulent region where solar particles and interstellar matter interact. Finally comes the heliopause itself, the balance point. These layers together form a complex dynamic structure, shaped not only by the sun but also by its motion through the galaxy. The heliosphere itself is thought to be distorted into a teardrop shape, compressed in front where the sun ploughs into the interstellar medium and elongated behind like a comet's tail. Studying the heliopause is not easy. The Voyagers provided invaluable data, but they are only 2 points in a vast structure, like dipping 2 straws into an ocean and trying to map the whole. Other missions, like IBEX, the Interstellar Boundary Explorer, and the upcoming IMAP, the Interstellar Mapping and Acceleration Probe, study the heliosphere indirectly, measuring energetic particles that flow back toward Earth. From these glimpses, we are beginning to piece together a picture of the Heliopause as a dynamic, ever-changing frontier, but much remains unknown. One of the mysteries is how the heliosphere protects us from cosmic rays. These high-energy particles originating from distant supernovae and other violent events stream through the galaxy. The heliosphere acts as a kind of shield, deflecting some of them and reducing their intensity inside. But how effective this shielding is and how it varies with the solar cycle are questions still under investigation. Understanding this is not only a matter of curiosity. For future astronauts travelling beyond the heliosphere, exposure to cosmic rays could be a serious hazard. The Heliopause, then, is not just a scientific boundary, but also a practical one for human exploration. The crossing of the Voyagers also reminds us of the patience required to reach such distances. Launched in 1977, they travelled for 35 years before reaching the Heliopause. Even moving at more than 17 kilometers per second, their journey was long and slow by human standards. This underscores the scale of the solar system and the challenge of leaving it. To us, the planets may seem close together in diagrams, but the Heliopause shows how truly vast our star's domain is. There's also a symbolic dimension to the Heliopause. When Voyager 1 sent back data from beyond it, many people spoke of humanity's first step into interstellar space. Of course, the probe is still far from another star, still bound by the sun's gravity, but psychologically, the crossing felt like a milestone, a threshold that had been theorized but never experienced. It was as if, after centuries of staring at the sky, we had finally opened a door and taken one tentative step into the hallway beyond. The Heliopause also raises a subtle question. If the solar system extends all the way to the Oort Cloud, then in what sense have we left it by crossing the Heliopause? The answer depends on how we define boundaries. The Oort Cloud is gravitational. The Heliopause is energetic. One is about where the sun's gravity dominates, the other about where its wind does. Both are valid, but they tell different stories. Perhaps leaving the solar system is not a single event, but a series of crossings, each one marking a new kind of departure. The Heliopause is simply the first of these, on the road to true interstellar space. When we talk about leaving the solar system, it is easy to imagine dramatic leaps, rockets roaring, sails unfurling, spacecraft slinging around planets and racing outward. But once the first burst of excitement fades, we are left with a quieter, more sobering reality. Space is vast, and even at the highest speeds we can currently imagine, journeys to other stars are not measured in years or even decades. They are measured in centuries, millennia, sometimes tens of millennia. This is the slow ship problem, the challenge of patience in a universe that stretches far beyond the span of a human life. To understand the scale of the problem, consider the nearest star system, Alpha Centauri. It lies just over 4 light-years away. A light-year, as the name suggests, is the distance light travels in a year, about 9.5 trillion kilometers. 4 of those distances separate us from Alpha Centauri. If Voyager 1, the fastest and farthest spacecraft humanity has ever built, were headed in that direction, it would take more than 70,000 years to arrive. That is longer than the span of recorded human history, longer than the existence of civilization itself. Even if we built a craft 10 times faster, the journey would still require thousands of years. This kind of timescale is hard to grasp. Our daily lives are measured in hours and days, our societies in decades and centuries. Very few things we build are designed to last even 1,000 years, and yet, interstellar travel, by any method currently imaginable, requires patience across spans that dwarf our usual sense of time. It is not just a technical challenge, but a cultural one. How do we build something meant to outlast not only our lives, but perhaps our nations, our languages, and even our descendants' memory of why the journey began? This is why the idea of the slow ship is both fascinating and troubling. On one hand, it suggests that leaving the solar system is possible without waiting for miraculous technologies. We could, in principle, build a spacecraft with today's technology that would eventually reach another star. It would take tens of thousands of years, but it would get there. On the other hand, such timescales are almost meaningless to us as individuals. No human could ever live to see the arrival. No mission planners could ever expect to receive data from the destination. The slow ship becomes a paradox, technically possible, but practically unreachable. Still, there are ways to imagine working with such patience. One approach is to think not in terms of individuals, but in terms of generations. A spacecraft designed to last for millennia could be tended, repaired, and even inhabited by many generations of humans. This is the concept of the generation ship, a vast vessel large enough to sustain life indefinitely, with communities living and dying on board as the ship drifts between stars. The people who begin the journey would never see its end, but their descendants would. The ship itself would become a world, carrying not just a crew, but an entire society. Another approach is to imagine putting travellers into deep sleep, suspended for centuries until they awaken at the destination. This cryosleep idea appears often in science fiction, but it remains speculative in real science. We do not yet know how to safely put humans into stasis for long periods, let alone centuries. Yet the idea lingers because it promises to solve the problem of human impatience. If the crew could simply sleep through the voyage, they would experience the journey as though it took no time at all. But perhaps the most realistic approach to slow ships is not about people at all. It is about machines. Robotic probes, unlike humans, do not age, do not grow restless, do not need food or air. They can simply drift, silently and patiently across millennia. The Voyagers are already examples of this, moving outward year after year without complaint. A more advanced probe, designed with extreme durability, could be launched toward another star with the understanding that it might not arrive for many thousands of years. Future generations, or even future species, might one day receive its signal. In this way, the slow ship becomes less about us, and more about continuity, about leaving something behind that endures beyond our own lifespans. Still, even machines have limits. Electronics degrade under radiation. Power sources fade, mechanical parts wear out. Designing a spacecraft to last for tens of thousands of years is not trivial. Even our most durable structures on Earth, like the pyramids, have survived only because they are stationary and massive, not small machines drifting through harsh space. To build something that can function across such timescales would require engineering on a level we have barely begun to imagine. The slow ship problem also raises philosophical questions. If a spacecraft takes 70,000 years to reach its destination, what does that mean for the people who launch it? The world might change completely in that time. Civilizations rise and fall in far less. Languages evolve. Cultures shift. Species themselves adapt. Would the mission still have meaning thousands of years later? Would the message still be understood? Or would the ship become like an artifact buried in time, a relic of a people long forgotten even by their descendants? And yet, perhaps that is part of the point. Slow ships force us to think on scales larger than ourselves, larger even than our societies. They remind us that the universe is not built for human convenience. Stars are far apart, whether we like it or not. If we wish to travel among them, we must adapt our expectations to their scale, not demand that they shrink to ours. The slow ship is not a failure. It is a mirror, reflecting back to us the reality of space and the patience it requires. There are small ways in which humanity has already embraced the slow ship idea. The Voyagers, as mentioned, will take tens of thousands of years to pass another star. The Pioneer probes and New Horizons are on similar trajectories. They are not fast, but they endure. Their missions may be measured in decades, but their journeys are measured in millennia. Each is a tiny demonstration of the slow ship problem already underway. When people first realized how far the stars truly were, and how slow our rockets remained, it was natural to look toward a power source far stronger than chemical fire. The sun itself runs on nuclear fusion, releasing more energy in a second than all of human civilization has produced in its history. On Earth, the nuclear age began in the 20th century with the splitting of atoms, a discovery that brought both terrifying weapons and the promise of nearly limitless power. From the earliest days of nuclear science, some dreamers wondered if this energy could be used not for destruction, but for propulsion. If the energy bound up in the nucleus of atoms could be released in a controlled way, it might give us the speeds necessary to cross the vast spaces between stars. The simplest idea was nuclear thermal propulsion. Instead of burning chemical fuel, such a rocket would carry a nuclear reactor on board. The reactor would heat a propellant, usually liquid hydrogen, and that heated gas would then expand out of a nozzle to produce thrust. This method promised far greater efficiency than chemical rockets, because a reactor can operate continuously, and hydrogen atoms are much lighter than chemical exhaust molecules. In the 1950s and 60s, the United States tested such designs under programs like NERVA, the nuclear engine for rocket vehicle application. Real reactors were built, fired, and tested on the ground. They demonstrated that nuclear thermal rockets were feasible, producing high thrust with twice the efficiency of chemical engines. Yet they were never flown. Concerns about cost, safety, and politics stalled the program, and by the 1970s, the idea was shelved. Still, the concept has never gone away. Modern studies continue to explore nuclear thermal. Rockets and some space agencies even envision using them for missions to Mars. But for interstellar travel, even nuclear thermal propulsion may not be enough. Heating hydrogen with a reactor can push a spacecraft quickly around the solar system, but the efficiency may still fall short for the speeds required to cross light years. This is why more ambitious designs have been imagined, ones that use nuclear energy in more direct ways. One of the boldest was Project Orion, proposed in the late 1950s. Orion suggested propelling a spacecraft by literally detonating nuclear bombs behind it. A massive plate at the rear of the ship, cushioned by shock absorbers, would absorb the force of each explosion, pushing the craft forward. By repeating this process thousands of times, the ship could reach a significant fraction of the speed of light. Calculations suggested that a large Orion craft might even carry humans to nearby stars within a few centuries. It sounds outrageous, even reckless, to propel a ship with nuclear detonations. Yet the physics was solid, and engineers seriously studied the idea. Designs were drawn up, tests of scaled-down systems were conducted, and prominent scientists supported the project. But the political and environmental concerns were immense. The 1963 Partial Test Ban Treaty prohibited nuclear explosions in space, effectively ending Orion before it could begin. Even so, the dream lingers. Some see Orion as one of the few designs that could realistically propel a massive starship within known physics. It is a reminder that sometimes the path to the stars may require uncomfortable choices. Other nuclear concepts try to avoid such extreme measures. Fusion propulsion became a central focus in the 1970s. Unlike fission, which splits heavy atoms, fusion combines light ones like hydrogen into helium, releasing vast amounts of energy in the process. It is the reaction that powers stars, and harnessing it on Earth has been a goal of scientists for decades. If used for propulsion, fusion could provide continuous thrust over long periods, pushing a spacecraft to incredible speeds. The most famous fusion starship design was Project Daedalus, created in the 1970s by the British Interplanetary Society. Engineers and scientists collaborated to imagine a vessel that could reach another star within a human lifetime. Their design was enormous, a two-stage spacecraft weighing thousands of tons, powered by pellets of deuterium and helium-3, ignited by electron beams. The ship would accelerate for years, reaching up to 12% of the speed of light, fast enough to reach the nearby star Barnard star in about 50 years. The mission would be unmanned, sending back data as it flew past its target. Project Daedalus was never meant to be built. It was a thought experiment, an exercise in engineering imagination. But it showed that, in principle, fusion propulsion could make interstellar travel feasible. Later studies, such as Project Icarus in the 2000s, updated Daedalus with modern technology, exploring variations on fusion engines, pellet ignition, and magnetic confinement. All of these designs share the same core idea. Fusion offers the highest energy density of any reaction short of antimatter. If controlled, it could sustain a spacecraft across light years. The problem, of course, is that fusion remains elusive even on Earth. Despite decades of research, no reactor has yet produced more energy than it consumes. Until fusion power becomes practical for power plants, building a fusion engine for a starship remains in the realm of blueprints and dreams. Antimatter propulsion pushes the dream even further. Matter and antimatter annihilate on contact, releasing energy with 100% efficiency. A tiny amount of antimatter could, in theory, propel a spacecraft farther than thousands of tons of chemical fuel. Some starship blueprints imagine magnetic bottles holding clouds of positrons or antiprotons, carefully released to drive engines of unimaginable power. But antimatter is difficult to produce and nearly impossible to store in useful quantities. Current technology can create only nanograms at great expense, and containment requires complex electromagnetic fields. Still, the concept remains attractive, because nothing in known physics offers more efficient energy release. In all of these designs, one theme stands out. To build starships, we must think big, far bigger than any spacecraft yet launched. Project Orion imagined ships thousands of tons in mass, carrying entire crews and equipment. Project Daedalus envisioned construction in orbit, assembling massive fusion stages too large to launch from Earth. These are not small probes like Voyager. They are city-sized vessels, the kind of machines that would redefine what humanity is capable of building. If nuclear dreams give us the speed, then how do we imagine humans making the journey itself? What would it mean to live not on a planet, but on a ship, generation after generation, drifting between stars? The more we think about the challenge of distance, the more it becomes clear that speed alone may not solve everything. Even with nuclear engines or fusion drives, even with the boldest of starship blueprints, the distances to other stars remain daunting. 4 light-years to Alpha Centauri, 12 to Tau Ceti, hundreds to more distant neighbours. Unless we can travel at speeds close to light, journeys will take not years but centuries. And so the question arises, if no single crew could survive the whole voyage, then who would carry it through? This is where the idea of the generation ship comes in, an idea that has fascinated scientists and storytellers for nearly a century. A generation ship is not just a spacecraft. It is a world, large enough to hold thousands of people, with ecosystems, farms, and living spaces. It would be designed to sustain life indefinitely as it drifts between stars. The people who set out on such a journey would not be the ones to arrive. Their children, grandchildren, and great-grandchildren would be the ones to see the destination. For those born on the ship, the vessel itself would be home. The stars outside its windows would be their sky. The gardens and corridors their landscapes. Entire societies would live and die without ever stepping on a planet. The allure of this idea is easy to see. It offers a way to make interstellar travel possible without waiting for physics to provide faster engines. Instead of bending space-time or mastering antimatter, we work with what we already know, sustaining human communities. In theory, if we can create a closed system that provides food, water, and air, and if we can maintain it across centuries, then a generation ship could keep moving until it reaches another star. Time becomes less of a problem when life continues on board. Science fiction has explored this concept in endless ways. Stories imagine vast cylindrical habitats, like the O'Neill cylinders proposed in the 1970s, spinning to provide artificial gravity through rotation. They describe carefully balanced ecosystems where plants recycle carbon dioxide into oxygen, where water is endlessly purified and reused, where every material is conserved. They imagine cultures adapting to the reality of life in transit, developing traditions and philosophies that reflect their enclosed world. Some stories are optimistic, envisioning thriving communities that endure and eventually reach new planets. Others are darker, showing how isolation and time might lead to decline, forgetfulness, or even collapse before the destination is reached. For scientists, the concept raises practical questions. How large would a generation ship need to be? How many people would it require to maintain genetic diversity? How do you keep systems running for centuries without outside repair? Studies suggest that a population of at least several thousand might be needed to ensure healthy reproduction and cultural stability. The ship itself might need to be kilometers long, with artificial ecosystems large enough to buffer against failures. Redundancy would be crucial. Multiple farms, multiple power systems, multiple habitats, so that no single breakdown would doom the community. There is also the question of culture. On Earth, societies change dramatically in just a few generations. Languages shift, values evolve, governments rise and fall. On a generation ship, such changes would unfold in a closed environment. Would the mission's purpose remain intact after centuries? Would descendants still feel committed to reaching a planet they had never seen? Or would they view the ship itself as sufficient home? Some speculate that maintaining a sense of purpose would require careful cultural engineering, education, rituals, reminders of the mission. Others argue that the ship might evolve its own destiny, diverging from the original plan in ways no one can predict. The psychological challenges are equally immense. Living in a confined environment, knowing there is no outside world to visit, could shape human minds in unexpected ways. Some might thrive in the stability, finding comfort in the enclosed society. Others might struggle with the lack of freedom, the knowledge that their lives are bound to a vessel with no escape. Over centuries, such pressures could become defining aspects of the community. A generation ship would not only be a technical experiment, but a social one, testing what it means to live as a species cut off from the wider universe. Still, the appeal of the idea persists. It reflects something deeply human, the willingness to endure, to pass on a task we cannot finish ourselves. Our species has always built cathedrals, monuments, and projects that take longer than a lifetime. A generation ship is an extension of that impulse, a project measured not in decades but in centuries, sustained by the idea that some future generation will reap the benefits. In this way, it is both practical and symbolic, a testament to patience and persistence. The technology required for such a ship overlaps with technologies we already study for long-term survival in space. Closed ecological systems are being tested in laboratories where plants, animals, and microbes recycle resources in miniature environments. Experiments like Biosphere 2 in the 1990s tried to simulate entire ecosystems under sealed conditions with mixed success. Space agencies test regenerative life support systems on the International Space Station, learning how to recycle air and water efficiently. Advances in genetics, robotics, and material science may someday make it possible to sustain a habitat for centuries without resupply. Each step we take toward living sustainably on Earth or on Mars is also a step toward making a generation ship feasible. Of course, such a ship would not need to carry only humans. Artificial intelligence and robotics could play crucial roles, maintaining systems, assisting with repairs, even guiding education and governance. Some designs imagine hybrid missions where humans live alongside AI caretakers, ensuring that knowledge and skills are preserved across generations. Others imagine ships starting empty of humans, carrying frozen embryos or genetic material to be raised by machines once a destination is reached. These variations blur the line between human presence and machine assistance, suggesting that the future of generation ships may be as much about cooperation with technology as about human endurance alone. When you step outside on a clear day and feel sunlight warming your face, it can be easy to think of light as something gentle, intangible, even weightless. Yet sunlight carries momentum. Photons, the tiny quanta of light, travel from the sun at nearly 300,000 kilometers per second, and though each one has no mass, they still carry energy and pressure. This pressure is so faint you cannot feel it standing in the daylight. But in the vacuum of space, with enough surface area, it can become a real force. In the same way, the sun also emits a constant stream of charged particles called the solar wind, invisible and steady. This wind shapes much of our cosmic environment, carving a bubble around the solar system and influencing every planet inside it. To leave the solar system, we have to understand not just gravity and engines, but the winds and light that wash across the void. The solar wind begins deep inside the sun, where nuclear fusion fuses hydrogen into helium, releasing enormous amounts of energy. Most of that energy emerges as light, but some of it heats the sun's outer layers so intensely that atoms break apart into charged particles. These particles, mostly electrons and protons, escape the sun's gravity and stream outward in all directions, filling the solar system. At Earth's distance, the solar wind blows past us at around 400 kilometers per second, carrying 1 million tons of matter away from the sun every second. It is not like wind on Earth. It is thinner than the best vacuum we can create in a laboratory. But over vast distances, its effects accumulate, shaping magnetic fields, driving auroras, and forming the boundary of the heliosphere itself. For planets, the solar wind can be friend or foe. Earth is shielded by its magnetic field, which deflects most of the charged particles and channels some into the poles, where they create the shimmering curtains of auroras. Mars, with its weak magnetic field, is far less protected. Over billions of years, the solar wind has stripped much of its atmosphere away, leaving the planet cold and dry. Even at the edges of the solar system, where the wind slows and eventually meets the interstellar medium, its influence is still detectable. In this sense, the solar wind is one of the most important features of our cosmic neighborhood, shaping the conditions for planets and missions alike. But what if we could do more than endure the solar wind? What if we could use it? The idea of riding the wind is as old as sailing. On Earth, humans learned to capture the motion of air with cloth and wood, allowing them to cross oceans long before engines or compasses. In space, a similar idea has taken root. Instead of sails catching air, spacecraft might carry sails that catch light. These solar sails, vast and reflective, could be pushed forward by the gentle but constant pressure of sunlight. Over time, the acceleration builds, and the craft reaches speeds impossible for chemical rockets to sustain. The principle is simple. A photon strikes a reflective surface and bounces off. In doing so, it transfers momentum to the sail. The push is tiny, but it never stops. Unlike rockets, which consume fuel and then coast, the solar sail keeps accelerating as long as light falls upon it. Over weeks and months, the speed grows, eventually surpassing what rockets alone can achieve. This is why many scientists and dreamers believe sails might someday be the key to reaching interstellar space. The concept has already been tested. In 2010, Japan's Icaros mission became the first spacecraft to successfully deploy a solar sail in deep space. The sail, about 14 meters on a side, unfurled like a vast thin sheet of reflective material, thinner than a human hair. Once deployed, it used sunlight to alter its trajectory, proving that photon pressure could indeed provide propulsion. More recently, the Planetary Society launched LightSail 1 and 2, privately funded missions that demonstrated controlled solar sailing in Earth orbit. These experiments were modest, but they confirmed that sails can work. The question now is how far and how fast we can push the idea. Scaling up is both tempting and challenging. To accelerate quickly, a solar sail must be both enormous and incredibly light. Some designs imagine sails hundreds of meters, even kilometers across, made of ultra-thin materials like aluminized plastic or graphene sheets. Building and deploying such structures in space would require new engineering methods, perhaps manufacturing directly in orbit, rather than launching from Earth. But if achieved, the rewards could be immense. A sufficiently large sail could, in theory, reach speeds of tens of thousands of kilometers per second, allowing travel to nearby stars within centuries rather than millennia. An even more ambitious variation involves not just sunlight, but lasers. In this concept, giant arrays of ground-based or orbital lasers would focus beams on a small reflective sail, driving it forward with far greater intensity than sunlight alone. The Breakthrough Starshot initiative has proposed using this technique to send gram-scale probes to the Alpha Centauri system within decades. Tiny spacecraft, no larger than chips, would ride laser-push sails to a fraction of the speed of light, reaching our nearest stellar neighbour in just over 20 years. The challenges are staggering, generating and aiming such powerful lasers, building sails strong enough to withstand acceleration, and protecting delicate electronics from radiation. Yet the idea remains one of the most concrete pathways humanity has considered for actual interstellar travel. The solar wind itself might also be used in more direct ways. Some have proposed magnetic or electric sails, devices that use fields rather than fabric to catch the charged particles streaming from the sun. A magnetic sail could deploy a large superconducting loop, creating a magnetic field that interacts with the solar wind, pushing the spacecraft outward. An electric sail, on the other hand, would extend long charged wires that repel solar wind particles, providing thrust. These concepts are still experimental, but they suggest that both light and wind might someday become tools for our journey outward. But gravity too can be harnessed. If rockets give us the first push, and sails give us patient endurance, then gravity itself offers something even more surprising. It offers a free ride. Not free in the sense that no planning or energy is required, but free in the sense that no fuel needs to be burned to gain the benefit. For as long as people have thought about long journeys through space, they have wondered whether it might be possible to simply sleep through them. Instead of building vast cities that drift among the stars, instead of handing down the mission to children and grandchildren, what if the crew could simply close their eyes and wake up centuries later at the destination? It is an idea that has appeared again and again in stories, from early science fiction novels to modern films. The word cryosleep is often used, though other terms appear too. Stasis, suspended animation, hibernation, all point to the same dream, finding a way to pause life, to slow or stop the processes of the body, and then to restart them safely after long spans of time. The appeal of this idea is obvious. If it worked, it would solve one of the central challenges of interstellar travel, the mismatch between human lifespans and cosmic distances. Instead of building self-sustaining societies, instead of asking generations to live and die in transit, a ship could carry a single crew who would close their eyes at departure and open them only when the journey was done. The experience for them would be seamless, as if the distance between stars had been compressed into a single night of sleep. The roots of this dream are not only in fiction. In nature, there are examples of organisms that slow their metabolism dramatically to survive long periods without food or in harsh environments. Bears hibernate through winter, lowering their body temperature and conserving energy. Certain frogs can survive being frozen solid, their cells protected by natural antifreeze chemicals, only to thaw and return to life in spring. Some tiny creatures called tardigrades can dehydrate completely, entering a state of suspended animation that lasts for years before reviving when water returns. These examples suggest that biology is more flexible than we sometimes imagine, capable of pausing and restarting in ways that seem almost miraculous. Scientists have long wondered whether similar techniques could be applied to humans. In medical emergencies, lowering body temperature has been used to slow metabolism and protect tissues. Patients undergoing certain surgeries are sometimes cooled to reduce the risk of damage when blood flow is interrupted. Experimental techniques called therapeutic hypothermia have been tested to preserve people after cardiac arrest, giving doctors more time to intervene. These are not true suspended animation, but they hint that the body can tolerate slowed processes under the right conditions. Research continues into induced hibernation or torpor for longer periods. NASA, for example, has studied the possibility of placing astronauts in torpor for weeks or months during long missions, such as journeys to Mars. The idea is that lowering metabolism and keeping crew members in a sleep-like state could reduce resource use, psychological stress, and the challenges of living in confined spaces. Instead of needing food, exercise, and constant activity, sleeping astronauts could simply rest until they were needed. These studies are still in early stages, but they show that the idea of cryosleep is not purely fantasy. It is being taken seriously as a possible tool for spaceflight. Still, the gap between weeks and centuries is immense. Putting a human into stasis for decades or longer requires more than just cooling. Cells must avoid damage from ice crystals. Metabolism must be slowed without shutting down critical functions. The immune system must be preserved. Memories must remain intact. Tissues must avoid degradation. The challenges are enormous. In many ways, the idea of cryosleep for interstellar travel is far beyond our current knowledge of biology. Yet the dream persists because it offers such a clean solution to the slow ship problem. Even if perfect suspended animation remains out of reach, there are variations that could still be useful. Slowing metabolism to a fraction of normal, even without stopping it completely, could extend human tolerance for long voyages. Combined with robotic caretakers and regenerative medicine, Such techniques might allow crews to endure journeys measured in decades. In this way, cryosleep need not be absolute. It could be partial, a matter of buying time rather than erasing it. There are also imaginative possibilities beyond biology. Some futurists have suggested that consciousness itself could be stored and reawakened, perhaps through mind uploading or advanced neural preservation. In such scenarios, the body might not need to endure centuries. Instead, the patterns of thought could be preserved in machines or in frozen tissue to be revived later. These ideas are speculative, perhaps even more so than biological stasis, but they reflect the same desire to carry a self across time without experiencing its full weight. Of course, cryosleep raises not only scientific, but ethical questions. If people are put into stasis, who decides when they wake? What if the ship malfunctions? Or if caretakers change their plans? What if the sleepers are never awakened at all, drifting forever between stars? Such questions appear often in stories, reflecting the unease that comes with surrendering control. To sleep through centuries is to trust completely in the systems and people maintaining the ship. It is an act of faith as much as of science. Yet the idea also carries a kind of comfort. Imagine closing your eyes in one world and opening them in another, with no awareness of the years in between. For the traveller, the distance would vanish, the impossibility of lifespans, compared to cosmic distances, would dissolve. Cryosleep transforms the universe from too large to manageable, at least from the perspective of human experience. It allows us to imagine living among the stars without becoming entirely new kinds of beings. For now, cryosleep remains a dream. No one has ever been placed into suspended animation for more than brief periods, and the leap from hours or days to centuries is vast. But research continues, inspired not only by space travel but also by medicine. The ability to preserve organs, tissues, and even whole bodies for long periods could revolutionize transplants and emergency care. In this way, the pursuit of cryosleep is not only about distant stars but also about saving lives here on Earth. Progress in one area may feed into the other, slowly bringing the dream closer. For most of human history, when people imagine voyages to the stars, they imagine people on board, brave explorers gazing through windows at the distant lights, steering their ships through the darkness, building new homes far from Earth. But as our understanding of distance and time has deepened, another possibility has emerged. What if the first travellers beyond our solar system are not humans at all? What if they are machines, guided not by living minds but by artificial ones? In many ways, it may be easier for artificial intelligence to endure the silence, the patience, and the centuries required to reach another star. Machines do not need food or water. They do not age or grow restless. They do not suffer from boredom or loneliness. With the right design, they can function tirelessly for decades or centuries, maintaining themselves as they drift outward. Already, the farthest human-made objects are robotic spacecraft, not human-crewed vessels. Voyager 1 and Voyager 2 are tiny examples of this truth, emissaries that carry our instruments and our messages into interstellar space. They are simple by today's standards, but they point toward a future where more advanced machines could carry the torch much farther. Artificial intelligence adds a new dimension to this idea. Today, AI systems can analyze data, make decisions, and adapt to changing circumstances. In a spacecraft, such abilities could be invaluable. Instead of relying on instructions sent from Earth which would take years to arrive once the craft is far away, an AI could operate independently. It could adjust its trajectory, repair itself, even decide which observations to prioritize. In effect, it could act as the mind of the mission, carrying human curiosity outward without requiring constant human attention. The advantages of such independence are clear. Communication across interstellar distances is slow. A signal to Alpha Centauri would take more than 4 years to arrive, and another 4 to return. For more distant stars, the delay would be decades. Human crews would struggle with such isolation, but an AI would simply continue working, patient and untroubled by the delay. In this way, artificial intelligence may be the natural first traveller to bridge the gap between stars. Some designs even imagine probes that combine AI with self-repair or self-replication. A sufficiently advanced machine could gather resources from asteroids or comets, using them to replace worn parts or build new probes. Over time, such machines could spread outward like seeds, each one carrying knowledge of Earth. This idea, sometimes called the von Neumann probe concept, suggests that once launched, a fleet of AI explorers could eventually fill the galaxy, even if humans themselves never left. Of course, the challenges are not small. Building machines that can endure centuries of radiation, cold and micrometeoroid impacts is no simple task. Electronics degrade, materials weaken, power sources fade. Even the best AI would be useless if its hardware failed. To make AI probes viable for interstellar travel, we would need breakthroughs in durability, self-repair, and long-term energy generation. But these are engineering problems, not impossibilities of physics. Unlike faster-than-light travel or exotic engines, AI probes fit squarely within the laws of nature we already know. There are also questions of identity and purpose. If an AI travels to another star and sends back data, does that count as humanity exploring? Some would say yes, because the machine carries our intentions and knowledge. Others might argue no, because without living humans on board, it is not truly us who have gone. This debate is less about technology than about meaning, about what it means to explore, and who gets to claim the journey. Even so, the prospect of AI as our first interstellar traveller carries a certain elegance. It reflects our strengths and our limitations. We are curious but fragile, ambitious but short-lived. Our machines, if designed well, can endure where we cannot. They can act as extensions of our senses, carrying our eyes and ears outward when our bodies cannot follow. In a way, AI probes are like the first scouts, paving the way for future human journeys, or perhaps standing in for them entirely. Already, projects like Breakthrough Starshot imagine tiny AI probes riding light sails, pushed by powerful lasers toward nearby stars. These would not carry humans, but microchips with cameras, sensors and processors. If successful, they could reach Alpha Centauri within decades, sending back images of alien worlds. For the first time, humanity would see another star system up close, not through telescopes, but through the eyes of machines we built. Such missions may not be as dramatic as crude starships, but they could be the true beginning of interstellar exploration. There is also the possibility that AI probes could outlast not only individuals, but entire civilizations. Imagine a probe launched in the 21st century, drifting for millennia. On Earth, cultures change, nations rise and fall, languages evolve, yet the probe continues, carrying the same mission, the same data, the same memory of who launched it. In this sense, AI travelers could serve as time capsules, preserving fragments of humanity long after we ourselves have changed beyond recognition. They would be both explorers and archivists, carrying our stories across time as well as space. But there are risks too. AI probes are only as wise as the instructions we give them, and only as stable as the safeguards we design. If a self-replicating probe were built without careful limits, it could in theory spread uncontrollably, consuming resources as it multiplied. Some call this the grey goo problem, though it is more often discussed in the context of nanotechnology. It is a reminder that exploration is not only about possibility, but also about responsibility. Sending AI into the galaxy would mean trusting machines with choices we might not fully predict. And yet, perhaps this is fitting. Just as we once sent human explorers into the unknown oceans, knowing they might face dangers beyond our control, so too might we someday send AI into the interstellar dark, trusting them to adapt and endure. The risks are real, but so is the potential. To hesitate forever would mean never leaving. To trust in machines may be the compromise that makes departure possible. Beyond the Oort Cloud, beyond even the imagined backyard fence of the solar system, lies the realm we often call interstellar space. And when we lift our gaze from home and look outward into that vastness, it is natural to wonder who lives closest to us in this cosmic neighbourhood. The answer is a small group of stars just over 4 light-years away, the nearest neighbours to the Sun. To us they are tiny points of light, barely visible to the naked eye in southern skies. But to astronomers they are familiar friends, studied for centuries, imagined as destinations for decades. Their names are Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, the closest stars to Earth beyond our own Sun. The Alpha Centauri system is not one star, but three. Two of them, Alpha Centauri A and Alpha Centauri B, form a binary pair. They orbit each other every 80 years or so, moving in an intricate dance that has been carefully charted since telescopes were first turned toward them. The third, Proxima Centauri, is a small red dwarf that drifts much farther away, loosely bound to the pair. It is Proxima that holds the title of the nearest star to Earth, at about 4.24 light-years. In cosmic terms, this is close, the stone's throw compared to the size of the galaxy. Yet in human terms, it is unimaginably distant, requiring tens of thousands of years to reach with current spacecraft. Alpha Centauri A and B are both similar to the Sun in many ways. Alpha Centauri A is a little larger and brighter, a yellow star slightly more massive than the Sun. Alpha Centauri B is a little smaller and cooler, an orange star with slightly less mass. Together they make a striking pair, orbiting in a way that creates changing distances between them. At their closest, they are only about as far apart as Saturn is from the Sun. At their farthest, they are separated by the width of Pluto's orbit. To an observer on a planet around one of them, the other star would shine in the sky as a brilliant companion, brighter than Venus appears from Earth. The system would never know true night. Proxima Centauri, by contrast, is faint and small, only a fraction of the Sun's mass. It is a red dwarf, the most common type of star in the galaxy, but so dim it is invisible to the naked eye. Red dwarfs burn their fuel slowly, glowing cool and faint for trillions of years. Proxima may outlive the Sun by a vast margin, still shining long after our star has burned out. Despite its faintness, Proxima has drawn intense attention in recent years because it is known to host at least 2 planets. One of them, roughly Earth-sized and located in the star's habitable zone, where liquid water could potentially exist. This planet, Proxima b, has become one of the most tantalizing targets in the search for life beyond the solar system. The discovery of Proxima b in 2016 sparked a wave of excitement. Here was a planet just 4 light-years away, orbiting the nearest star, potentially rocky, potentially temperate. It is not Earth, and conditions there may be harsh. Proxima is an active star, prone to flares that bathe its planets in radiation. The planet is likely tidally locked, with one side always facing the star, and the other always in darkness. Yet despite these challenges, the possibility remains that some form of life could exist there, adapted to its unique environment. For scientists and dreamers alike, Proxima b has become a symbol of what might be waiting just beyond our reach. Alpha Centauri A and B have also been studied for signs of planets, though detecting them is difficult. The brightness of the stars and their close orbit complicate observations. Still, some evidence has hinted at possible planets, and astronomers continue to search with increasingly sensitive instruments. If planets exist around Alpha Centauri A or B, they would be remarkable destinations, orbiting stars much like our Sun. Imagining a planet with 2 suns rising and setting in its sky is no longer just the stuff of fiction. It could be real, waiting less than 5 light-years away. For centuries, Alpha Centauri has been a source of curiosity. To ancient cultures in the southern hemisphere, it was part of the Centaurus constellation, a marker in the sky. To European explorers, it became a navigational star, guiding ships across oceans. To modern astronomers, it is both familiar and mysterious, close enough to study in detail, yet far enough to remain just out of reach. The fact that it is the nearest system has made it a constant focus of interstellar imagination. If we ever send a probe beyond the Oort Cloud with the intention of visiting another star, Alpha Centauri will almost certainly be the first target. The distances involved remain daunting. Light from Alpha Centauri takes just over 4 years to reach us, but for a spacecraft like Voyager, the journey would last more than 70,000 years. To make the trip in a human lifetime would require speeds of at least 10% the speed of light, something far beyond our current engines. Yet the proximity of Alpha Centauri makes it the most realistic target for projects like Breakthrough Starshot, which envisions tiny probes pushed by lasers reaching the system in just a few decades. If such missions succeed, the first close-up images of another star system could come from Alpha Centauri within the century. There is also a symbolic power in the name itself. Alpha Centauri is the nearest bright star to the Sun, visible in southern skies, often imagined as the first stepping stone into the galaxy. Proxima, though faint, is closer still, the hidden neighbour we only recently discovered to be more interesting than we ever expected. Together, they form not just a star system, but a symbol of possibility. They remind us that the stars are not abstract points of light, but real places with real planets, real skies, and perhaps real life. The allure of Alpha Centauri lies in its familiarity and its mystery. We know it is close, we know it has planets, and yet we cannot yet reach it. It is like a distant shore seen across an ocean, tantalizingly near, yet separated by waters too deep to cross with current ships. When we confront the distances between stars and galaxies, the challenge seems almost absolute. Tens of thousands of years to reach even the closest systems with today's technology, millions to cross between galaxies. It is natural then to ask whether there might be another way. Instead of moving faster through space, what if space itself could be reshaped? Physics does not offer easy answers, but it does offer possibilities, ideas that hover at the edge of science and imagination. These are the concepts of wormholes, warp drives, and other theoretical pathways that might one day allow us to cheat the immensity of the cosmos. The idea of a wormhole comes directly from Einstein's theory of general relativity, which describes gravity as the curvature of space-time. In this framework, space is not a static stage, but a fabric that can bend and stretch. A wormhole is a hypothetical tunnel through that fabric, connecting two distant points with a shortcut. Imagine folding a sheet of paper so that two dots on opposite ends touch. A wormhole would be like punching a tunnel through the fold, allowing travel between the dots in far less distance than sliding along the surface. Mathematically, wormholes are allowed by Einstein's equations. In principle, the geometry of spacetime could create such shortcuts. The problem is that wormholes are unstable. Left alone, they would collapse almost instantly, closing before anything could pass through. 2. Hold one open would require a form of matter with negative energy density, often called exotic matter. Such matter has never been observed in the quantities needed, though tiny effects resembling negative energy appear in certain quantum phenomena. Without exotic matter, wormholes remain only mathematical curiosities. Even if a stable wormhole could exist, many questions remain. Could it be created, or only found? If created, how would we shape spacetime on such scales? If found, how would we know where it leads? Could it connect not just places in space, but also times, creating paradoxes of causality? These uncertainties place wormholes firmly in the realm of theory, fascinating but speculative. Still, they remain one of the most enticing ideas for interstellar travel, a way to leap across the galaxy without ever crossing the space in between. The warp drive is another concept that emerges from general relativity. Instead of tunneling through space-time, it envisions bending space-time around a ship. In 1994, physicist Miguel Alcubierre proposed a model in which a spacecraft could sit inside a bubble of flat space, while the space in front of the bubble contracts and the space behind expands. The ship itself would not move faster than light within its bubble, but the bubble could move faster than light relative to the outside universe. In this way, the warp drive circumvents the cosmic speed limit, not by breaking it, but by moving space itself. The Alcubierre drive is elegant on paper, but like wormholes, it requires exotic matter with negative energy to function. The amount needed in early calculations was astronomical, more mass energy than existed in the entire universe. Later refinements reduced the requirement, but it remains immense, far beyond anything we can produce. There are also questions of stability. How would the bubble be created? How would it be steered? Would radiation build up at the bubble's edges, frying anything at the destination? These obstacles keep the warp drive in the category of theory, not engineering. But the fact that the equations allow it is enough to inspire imagination. The allure of these ideas is not just in their practicality, but in what they represent. They remind us that space and time are not absolute, not rigid. They are dynamic, capable of bending, stretching, and twisting in ways that defy everyday intuition. If the universe allows such structures, then perhaps one day they could be used. Even if wormholes and warp drives remain forever out of reach, their study teaches us more about the nature of space-time itself, about the limits of physics, and the possibilities beyond. Science fiction has embraced these concepts eagerly. Wormholes appear as portals connecting distant worlds, from the tunnels of Stargate to the passages of Interstellar. Warp drives are the backbone of Star Trek, allowing ships to cruise the galaxy in hours. These stories may not reflect real engineering, but they serve an important role. They give us metaphors for thinking about distance, ways to imagine bridging gaps that otherwise seem hopeless. They inspire scientists as well as audiences, planting seeds of ideas that may someday sprout into real discoveries. But it is important to hold two truths at once. Wormholes and warp drives are allowed by our current theories of physics, but they remain entirely hypothetical. No evidence for them has ever been found. No path to building them is yet clear. To count on them as solutions would be premature, yet to dismiss them entirely would be equally narrow. Many breakthroughs in science began as ideas that seemed impossible, only to become real centuries later. Wormholes and warp drives may remain dreams forever, or they may someday prove to be the doors we need. For now, they are reminders of how much we do not yet know. They also force us to confront deeper questions. If such shortcuts exist, are they safe? Could they allow not just travel but communication across the galaxy, altering the way civilizations connect? Might they explain mysteries we already see, like unusual astrophysical phenomena? Could they even be dangerous, creating paradoxes of time or unleashing energies we cannot control? In this sense, wormholes and warp drives are not just engineering problems, but philosophical ones, touching on the nature of causality, reality, and safety in a universe far stranger than it appears. For now, our ships remain slow, our journeys patient. But the realm of theory is valuable precisely because it stretches our imagination. It reminds us that the laws of physics are not yet complete, that the universe may hold pathways we have not yet glimpsed. Whether wormholes or warp drives ever leave the blackboards of physicists, they serve as mental wormholes of their own, shortcuts to broader thinking, expansions of what we consider possible. And from these speculations, the mind drifts naturally to another question. If wormholes and warp drives are possible, even in theory, then what might it mean for civilizations older than ours? For all the dreams we spin about sails driven by sunlight, ships powered by nuclear fire, or tunnels through space-time itself, there lingers a quieter possibility. What if we never leave? What if humanity never sends crewed vessels beyond the solar system, never plants a flag on a planet circling Alpha Centauri, never sails the galaxy as countless stories have imagined? At first, this idea may sound disappointing, even bleak. But when we look closer, it becomes something more complex and perhaps even comforting. For the truth is that we are already explorers, and leaving the solar system may not be the only way to fulfill that part of ourselves. The reasons why we might never leave are many. The first is simply distance. Stars are far, unimaginably so, and even the nearest ones demand patience far beyond human lifespans. Every technology we have proposed, from rockets to sails to fusion, drives, runs up against this same barrier. Unless physics offers shortcuts, the gulf between stars may simply be too great for us to cross in person. We may always be bound to our own neighborhood, limited not by imagination but by the scale of the cosmos itself. There are also the challenges of survival. Space is harsh in ways we are only beginning to understand. Radiation seeps into every corner beyond Earth's magnetic field. Life support systems must work perfectly for years without fail. Tiny meteoroids, invisible specks of dust, move at speeds that can pierce metal. For journeys lasting centuries, these dangers multiply. Perhaps the human body, evolved for Earth is simply not built for such journeys, and no amount of engineering can fully protect it. Then there are the social and cultural challenges. A generation ship may be possible in theory, but would people truly agree to live and die inside a vessel with no chance of return? Cryosleep may someday be imagined in laboratories, but could we ever entrust our lives to centuries of sleep? Even if the technology exists, the will might not. Humanity is often ambitious in vision but cautious in practice. We may prefer the safety of robotic explorers and the security of home to the uncertainty of becoming a truly interstellar species. There is also the question of priorities. Even as we dream of other stars, Earth demands attention. Our planet faces challenges of climate, resources, and survival that are immediate. The energy and resources required to build a starship could transform life here at home. Some argue that our duty is not to flee into the galaxy, but to tend to the world we already have, to ensure that Earth remains habitable and vibrant. In this view, the dream of leaving may be a distraction, a temptation to look outward instead of inward. And yet, to say we might never leave is not the same as saying we cannot explore. Already, our robotic emissaries have left the solar system. Voyager 1, Voyager 2, Pioneer 10 and 11, New Horizons. They are tiny, but they are proof that we have extended our reach. Our telescopes peer into distant galaxies, revealing worlds billions of light years away. In a sense, we are already an interstellar species, not in body but in mind. Our curiosity has crossed the distances even if our ships have not. This is why the thought of never leaving is not necessarily sad. We may not need to cross the gulf physically to be explorers. We are already receiving signals from the edge of the universe, already deciphering the light of planets orbiting other stars, already sending our voices into the dark on golden records. Exploration is not only about footsteps, it is also about awareness, imagination, and understanding. In those ways, we have already gone farther than any generation before us could have dreamed. There is also humility in accepting limits. Perhaps the stars are not meant to be colonized by us. Perhaps our role is not to spread endlessly, but to cherish what we have. Earth is rare, precious, and fragile. To remain here, to care for it, may be as noble as to leave. The dream of departure can inspire us, but the reality of staying can ground us. Both are valuable. Both remind us of what it means to be human. Even if we never build a ship that carries people to another star, we may still leave our mark. Our probes may drift forever, silent ambassadors of a species that once looked up. Our signals may spread outward, faint ripples in the cosmic sea. Perhaps somewhere far away another intelligence will detect them long after we are gone. In that sense we will have left, not with bodies but with voices, not with colonies but with echoes. And there is another comfort in the possibility of never leaving. It frees us from urgency. If the stars are beyond us, then we can focus on the present. We can explore in ways that are possible now, with telescopes, probes, and imagination. We can build worlds in stories and dreams without needing to risk lives or resources beyond what we can bear. The galaxy can remain a source of wonder rather than a task to be completed. We can love it from afar, as one might love a landscape glimpsed from a mountain, beautiful precisely because it cannot be owned. This does not mean the dream fades. The dream of leaving has always been part of us, whether or not it is ever realized. It fuels art, science, and philosophy. It shapes how we see ourselves, small creatures on a small planet, yet capable of thinking across billions of years. The dream matters even if the journey never happens. It reminds us that we are curious, restless, and imaginative. In that sense, it is already fulfilling its purpose. So perhaps we will never leave. Or perhaps we will, centuries from now, when technologies we cannot yet imagine make it possible. Either way, the stars will remain patient and shining. They do not demand that we come. They simply invite us to wonder, and that may be enough. And yet, even as we accept the possibility of never leaving, another thought arises. What if one day, despite all the challenges, we do find a way? What if the dream persists long enough, and the ingenuity of future generations proves greater than we expect? In that case, the final question will not only be whether we can go, but why we should. There is a special kind of quiet that comes at the end of a long day, when the tasks are finished and the noise has settled, when even the hum of your own thoughts seems softer. It is in those moments that looking up at the night sky feels different. The stars are the same as they always are, but your mind is gentler, more open, more ready to drift. Perhaps you have had that feeling yourself, lying back in the dark, seeing pinpoints of light scattered overhead, and letting your thoughts expand outward until the world around you feels both enormous and intimate all at once. That is the feeling we have carried together through this story, the long wondering of whether we could ever leave our solar system and what it might mean if we did. The stars above are easy to take for granted. They appear every clear night, patient and unchanged, whether we notice them or not. Yet behind that quiet glow lies everything we have been talking about. Distances that bend the mind, possibilities that strain imagination, ships that might one day carry not just instruments but stories, voices, or even entire communities into the deep dark. To look at the stars is to see both a ceiling and a doorway, both a comfort and an invitation. And even when we do not move toward them, even when our feet remain here on Earth, they change us simply by being there. Perhaps you have felt that change before, a night when you looked up and realized how small Earth is compared to the sky, a night when you felt both insignificant and deeply connected. That tension is something we all carry, and it is part of why questions like leaving the solar system matter. It is not only about engines, rockets, or physics. It is about who we are when we ask. It is about recognizing that the curiosity to wonder what lies beyond is just as much a part of us as the need to sleep, to dream, to rest. Even now, as you listen, spacecraft we built are still moving outward, carrying faint signals from the edge of the heliosphere, carrying golden records that whisper greetings into a silence too vast to imagine. They will continue long after we are gone, drifting patiently, reminders of a species that once looked up and decided to reach. They are small, but they are also everything. They carry not just instruments, but the proof of our desire to extend ourselves into the unknown. To know that they exist is to know that we have already started the journey, even if we never complete it. And what of us here under the stars? Maybe we will never leave. Maybe we will. Either way, the sky is not going anywhere. It will be there tomorrow, and the night after that, and for generations to come. Its presence alone can be enough to calm the restless parts of the mind. If leaving is impossible, the stars still belong to our thoughts. If leaving is possible, they will still wait patiently for us to arrive. Either way, we cannot lose them. They are ours to wonder about, to measure, to admire, to dream toward. Think for a moment about the oldest humans who ever lived on Earth. The largest structure in the universe resembles things we see on the smallest scales, a reminder that patterns echo across levels of reality. The size of these filaments defies ordinary comprehension. A single filament can span 500 million light-years. Within it are hundreds of thousands of galaxies, each galaxy containing billions of stars. The light from one end would take 500 million years to reach the other. To give a sense of proportion, when the dinosaurs roamed Earth, light that is only now reaching us may have been leaving galaxies on the far side of such a filament. Immensity here is not only distance but time, stretching across ages far beyond human history. One of the largest known structures is the Hercules Corona Borealis Great Wall, a filamentary supercluster complex over 10 billion light-years away. It is estimated to be about 10 billion light-years in length, making it the largest single structure ever identified. That distance is so great that the light from it has been travelling toward us for most of the history of the universe itself. We see it not as it is now, but as it was billions of years ago. Even calling it a structure can feel misleading, because on such scales the universe itself is expanding, and the thing we name may already have stretched or changed beyond recognition. Yet it stands as a marker of immensity, one of the farthest reaches of size that we can describe. The cosmic web forms because matter was not distributed evenly in the early universe. Tiny fluctuations in density after the Big Bang grew over billions of years as gravity pulled matter into slightly denser regions. which in turn attracted more matter, amplifying the pattern. Dark matter, invisible but abundant, played a key role, creating gravitational scaffolds upon which gas and galaxies gathered. The filaments we see today are the result of that process, threads drawn out of initial ripples magnified into cosmic highways of structure. The web is not just arrangement, it is history, written across billions of years. Dark matter itself remains unseen, but its effects are everywhere. Simulations of the universe, starting from the physics of the Big Bang and the laws of gravity, recreate the cosmic web with stunning accuracy. When you compare the maps of real galaxies to the simulated patterns of dark matter, they match. The web is not an accident. It is the natural outcome of physics acting on scales so large that galaxies themselves become mere details in the pattern. The immensity of the web is not only its size, but its inevitability. What is striking about the cosmic web is that it gives the universe texture. Instead of being a bland expanse, it is a tapestry of density and emptiness, light and darkness, filaments and voids. If you could somehow step outside and look back, you would see it stretched like lace, glowing threads across a black background. Galaxies would no longer be the focus. They would be beads on the strings, ornaments on the filaments, details in a far larger design. The immensity is not in the galaxies themselves, but in their arrangement, in the way they trace invisible scaffolds of matter and gravity. Voids are as important as filaments. These vast, empty spaces make up most of the universe, regions where galaxies are sparse or absent. A void can be 300 million light-years across, a bubble of near nothingness in a universe of structure. Their immensity lies not in what they contain, but in their emptiness. To drift into such a region would be to leave behind the glow of galaxies and enter darkness, with only occasional faint light scattered across incomprehensible distances. The contrast between filament and void, presence and absence, gives the cosmic web its form. When we look at images of the web, it is tempting to see design. The branching threads, the clustering nodes, the vast symmetry. It looks deliberate, but it is the product of natural laws, of simple physics unfolding over time. The immensity does not require intention. It arises from gravity, expansion, and the seeds of quantum fluctuations stretched by cosmic inflation. The web is immense not only in size, but in the simplicity of its origin, a pattern that emerges inevitably when the universe is allowed to evolve. And yet, as immense as the cosmic web is, it too is bounded. What we can see of it is limited by the observable universe, the region from which light has had time to reach us since the beginning of the cosmos. Beyond that horizon, more filaments and voids almost certainly exist, but they are forever hidden from us, receding faster than light as space expands. The largest structure we can describe is limited, not by what exists, but by what we can see. Immensity becomes as much a question of perspective as of measurement. From Earth we can only see tiny slices of this web at once. A telescope captures a field of galaxies, each one a distant light, but it takes surveys across decades to piece together the larger picture. And even then, what we build are maps, reconstructions, models of what the universe looks like at scales so vast that no single human mind can hold them directly. The immensity of the web is not only spatial, it is cognitive, a challenge to imagination, a demand that we stretch our sense of scale to the breaking point. Perhaps the most humbling thought is that everything we know, every galaxy, every cluster, every filament, is only part of one cosmic web. The universe may be infinite. There may be other webs, other structures beyond what we can observe. Or perhaps the observable web is all there is, and its immensity is the limit. Either way, we're left with a picture of scale that dwarfs every earlier step. When we look at the cosmic web, it is the glowing filaments and the bright clusters that capture attention. They are the threads of light, the scaffolds of galaxies, the places where matter gathers and stars are born. But between those threads lie the voids, immense regions of space where almost nothing exists. If the filaments are the walls of the universe, think about the countless generations before them. All of them looked up at the same stars you see now. None of them ever left the solar system, yet they still felt wonder, they still told stories. They still carried the light of those stars into their art, their songs, their memories. You are part of that same line, continuing it in your own way. Whether you are listening from a city where the sky glows faintly, or from a quiet place where the stars are sharp and clear, you are participating in something vast and ancient simply by noticing. It is a reminder that exploration is not only about crossing physical space. It is about expanding awareness. When we imagine starships or sails of light, we are doing what humans have always done, stretching the boundaries of thought. Sometimes that stretching takes us to real voyages, across oceans or into orbit. Sometimes it takes us to imagined voyages, into stories that sustain us. Both matter. Both keep us curious. Both remind us that we are more than just the daily routines that fill our time. And now, as you prepare to rest, it may be comforting to hold on to that thought. The universe is unimaginably large. The stars are unimaginably far. And yet here you are, safe and present, able to think about them from the quiet of your own life. That is not small. That is enormous in its own way, because in that act of thinking, of imagining, of allowing your mind to drift outward, you have already travelled farther than your body ever could. You have already left Earth, not in reality but in spirit, and sometimes that is enough. So as your eyes grow heavier, imagine yourself lying beneath the stars. Imagine the faint light of Proxima Centauri, just over 4 years away, already reaching you across the void. Imagine the glow of Andromeda, 2.5 million light-years away, still visible as a smudge in the sky. Imagine the arc of the Milky Way itself, stretching above you, a reminder that you are inside something vast, spinning and shining. Each light is a reminder that distance does not erase connection. Each one is a silent greeting across time. You do not need to leave the solar system tonight. You do not need to solve the problem of distance or invent new physics. You only need to rest, to let curiosity keep you company as you drift towards sleep. The questions will still be there tomorrow. The stars will still be there tomorrow. For now, it is enough to let them watch over you, constant and calm, while your thoughts soften and your breath slows. And if someday, far in the future, humanity does build ships that sail to other stars, remember that those journeys will have begun with nights like this, with people lying back, looking up, and letting their imaginations travel where their bodies could not. Exploration begins, not with engines, but with wonder. You are part of that beginning, and that is a good thought to carry with you under the stars as you close your eyes. Hello, and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines and the relentless rush of now, and step quietly into the vast, starlit corridors of cosmic possibility, where questions stretch back, not thousands of years but billions, where the story isn't written in history books or carved in monuments, but traced in the light of distant suns still travelling toward us across the void. Here, in this space between present and infinite, we wander together through one of humanity's oldest dreams. We stand at the edge of our solar system, that familiar neighbourhood of planets and moons and asteroid belts, and we ask a question that feels both simple and impossible. Can we ever leave? Can we slip beyond the sun's embrace, beyond the invisible boundaries that have held us since our species first looked up?